0 if L and L dashed are different. Okay? That just comes out. I mean, you could try showing that yourself, because you know expressions for the spherical harmonics. You know what a hat is. You know, but it's either this or this. You have expressions for that. It might be a bit tedious, but anyway, bottom line is this integral here is 0 unless L and L dashed are equal. Okay, so now we're down to three parameters. Okay, so in other words, L and L dashed cannot be chosen independently. If you choose an L, then the L dashed, like the L dashed here, has to be the same value as that L. All right. So, but your M's can still be, they're still independent. So your M here ranges between minus L and L, and your M dashed ranges between minus L and L. Okay? So for this, as if you can look on this as a kind of matrix, where the size of the matrix now will be, if you think about it, now this M would correspond to like here, and this M dash would correspond to here. Now this M, because it's the angular momentum, the z, it's the eigenvalue of the z component of the angular momentum, and that M can range over minus L to L. Right? You can take 2L plus 1 different values, and the M dash here similarly, but independent. M dash is independent of M. So this effectively, this M here can have 2L plus 1 different values. This N here, which is M dashed, can also have 2L plus 1 different values. So this then is one element of this, well, you look on this as a matrix element, and that matrix is of size 2L plus 1 squared. Follow that? Because you can have 2L plus 1 different values of M here, and you can have 2L plus 1 different values of M dashed. So the matrix that corresponds to this is of size 2L plus 1 squared. Okay? Now, you're talking about representations of this operator. So you can choose, you can choose what spherical harmonic do you want to choose? Well, L has ranges from 0 to infinity, right? So you can have an infinite number of representations of this operator. What that means is you can have infinite number of these spherical harmonics here, right? For a given L. You choose an L, that fixes the 2L plus 1, that fixes the size of your matrix here. You know, this then becomes an, well, here, I put the equivalent of this. So this, look on this as a matrix element. And you fix the L, that determines the size of the matrix, or this where this integral here would become just one element of that matrix. A 2L plus 1 all squared size, square matrix. All right? That's what I'm saying here. So but doing this kind of thing, you fix the L. That using this gives you a 2L plus 1 squared matrix. And you use that set of matrices. They represent the operator here. And by getting higher and higher and higher values of L, you just have bigger and bigger matrices, which have the same algebraic properties as your operator. Okay, so you can represent your operator with ever larger 2L plus 1 squared matrices. Right? You can have an infinite number of these matrix representations. All right. Now let's actually start doing. Let's actually find some of these matrix representations. You know, using actual operators and actual spherical harmonics. All right. Well, let's take the simplest case when L is just 1. Right. The first non-trivial example. Well, if L is 1, then M can range over -1, 0, and 1. Okay, 2L plus 1. So you'll have, it's the smallest matrix representation for your operator. Let's see, what do we? Okay, let's choose for the operator A hat. Let's choose it to be the Z component of the AngularMmntm. So LZ hat, right? Now LZ hat was -I h bar d bar d phi. So plug that in here. Now here's your spherical harmonic here. Okay. Conjugated. Okay. Now note here you've got L and L. They have to be the same because if they're different, the whole thing just 0, right? So no representation, no matrix, it's just all zeros. Okay, so this L and this L here is similar, but the M's and M dash, they're different. Okay, here's your solid angle again. M and M dash independently range over the values 0 and plus or minus 1. So they can have 3 different values each. So you're talking a matrix of 3 by 3. Okay? So you have to calculate this matrix for L is 1 and M is -1, 0, plus 1, and for M dash also -1, 0, plus 1, right? So you get 9 different cases. For 7. For 7 of them, you get 0, and one value you get a 1 here. So when M is 1, M dashed is 1, you get that. Is that right? Or maybe this one? I'm not sure. Well, anyway, the equivalent matrix, the matrix representation, is of this form. Now look, it's diagonal, and we talked a bit about this earlier lecture. That's not surprising. It's because these eigenfunctions here, these spherical harmonics, are they're eigenfunctions. They're orthonormal. Okay, so you expect you know this is a differential operator, and then you'll get an eigenvalue m. You know, you'll get m times this because that's, you know, from the eigenequation. So and these are orthonormal. So if you get m from this, m times this, right? Because these wave functions, these spherical harmonics, are orthonormal, then you expect to get diagonal values. Now, so here is a matrix representation for L equals 1. It's a 3 by 3 matrix, right, with diagonal elements, and off-diagonal terms are 0. You expect that because of these spherical harmonics are orthonormal. Now, you know, around our board, we're leading into the mathematics now of spin. Now, do you notice now the size of these matrices? These matrices form a representation, an equivalent way of talking, if you like, equivalent language, of the operators here. So you can talk in terms of operators, you can talk in terms of matrices. Now these matrices here are all of odd size, right? They are 2L plus 1 squared matrices. So the size of these matrices is an odd number. Okay? So the question is, how about an even number? Could we have a matrix representation of an operator that's not 3 by 3 but an even number, like 2 by 2? And that's the lead-in, the hint to the concept of spin. So we'll spend the next few sessions talking about spin, because it's a very quantum mechanical phenomenon. Doesn't exist at all in classical mechanics. It's exclusively quantum mechanics And the mathematics of it is relatively simple and very interesting. And spin plays a very important role in the future in quantum mechanics. I'll stop there.